Okay, let us do a problem similar to the one before, but this time a little bit more complex because you will see that the Q is not zero. And I just want to make sure that I was going to cover when is the heat going to be a positive entropy or when it's going to be a negative entropy. It is pretty easy, but I just want to make sure that I do it using one example. So let's say steam enters a turbine. So this time a turbine, generally sketch with this symbol that you see is the reverse of the compressor. So the role of a turbine is generally to create power. All right, so this will be our turbine. One, really this should be one here, and let's say two here. So we know there is steam, the substance is steam. So we know the state is superheated. Turbines with a pressure P1 equal to 30 bars at a temperature of 400 degrees Celsius and a velocity of 160 meters per second. So state 1. Saturated vapor, so we know state 2 will be saturated gas or saturated vapor at T equal 100 degrees Celsius and exit at a velocity of 100 meters per second. At steady state, the turbine develops a work equal, so the work developed by this turbine here, so this will be our control volume, and this is going to develop work at a rate of 540, so this is power, kilojoules per kilogram. Okay, this is really work, but you will see it's really power per unit mass, or just power per mass would be the same thing over here, because the seconds would cancel on top and the bottom. Heat transfer between the turbine and its surroundings occurs at an average outer surface temperature of 350. Okay, so that's the difference with the previous problem. This time we have the Q, and let's say that the temperature over here, we're gonna say surface is 350 Kelvin. Okay, determine the change in entropy within the turbine per kilogram of steam flowing in okay, so in kilojoules, kilogram Kelvin. Neglect change in potential energy. Okay, so again, this problem is for the above problem. The first principle of thermodynamics becomes what? Q minus work plus H1 will be equal to H2. Okay? Okay, and I forgot actually something here. So let me just rewrite it. It's correct, but I'm missing one term. This would be neglecting the kinetic energy. So it would be minus this of the control volume plus H1 plus V1 square over 2 will be equal to H2 plus V2 square plus V2 square over 2. Okay, where we know that M equal M1 equal M2. Okay, so actually from this problem, what we need to find over here is what is the Q, and we need to find that per kilogram. So basically we divide all this stuff by the mass. We're gonna have what? Q minus plus, let's say, H1 minus H2 plus 1/2 V1 square minus V2 square will be equal to 0. So if we solve for Q over M dot, which will be the same as Q over M, we have what? And this will be the same as this one. So let's say it would be the dot plus H1 minus H2 plus so I need to move this one to the side, it will be H2 minus H1. Okay. Plus, let's see, I went too fast here, so we move to the other side. So this will be now plus 1/2 V2 squared minus V1 squared. Okay. So in this equation, what do we know? Alright, so out of that equation, we know that the work or the power per unit mass is equal to 540 kilojoules per kilogram. Alright, and we know that, let's do this term here, 1/2 V2 squared minus V1 squared is equal to what? 1/2 of V2 is equal to 100 meters per second square minus 160 okay, and we're going to need some minor unit transformation here, so 1 newtons equal 1 kilograms meter second square, and this is important one over here, 1 kilojoules equal 1000 newtons meters. Okay, so if we do this calculation here, I'm going to stop the video for a second to do the calculation. Okay, so this is equal to minus 7.8 kilojoules per kilogram. Okay, and we need now to find H1 and H2. So let's see, for H1 we know that it's steam, we know the pressure, we know the temperature. Okay, so in order to find the value, we know it's steam, so we can go directly to the superheated tables. So what we need to make sure is that state 1 is 30 bar, which is the same thing as 3 megapascals. Okay, so this will be this table over here. Okay, so it's not very clear, but 400 is right here. So if we go across, we should find the value for H. And you see the saturation temperature is 233. In this case, it's 400, so it's well above. So it should be here. H should be 3,231.7. And S will be 6.9235. Okay? And that's table A6. Let me zoom out again. So if I had to do a little figure here, and you know I like to do the TV. So if we are here at 30 bars, we are somewhere over here, and we're going to move over here over the saturation. So this will be our process over here. All right, so that was table, let me go back to the table A6. So from table A6, at P equal 3 megapascals, we have that T saturation equal to 233.85 degrees Celsius. So we know that T1 is higher than T saturation. So that means that we are above, that we are on the superheated. But we knew that they were telling us that it was steam. So at P equal 3 megapascals and T equal 400 degrees Celsius, what do we get? We get that H1 is equal to 3,231.7, and that S1 is equal to 6.9235. Okay, now for H, so this is for H1. Now for H2, we know it's saturated, so we need to go to the saturated tables, which is table A4, and we know the temperature. So temperature is 100. So we know that H2 will be equal to H gas, which is 2,675.6, and S2 will be equal to S gas, 7.3542. Okay? All right, so let me just write this down. So table A4 at T equal 100 degrees Celsius. I have that H2 equal to H gas equal to 2,675.6, and S2 equal to S gas, that will be equal to 7.3542. Okay. All right, so we did a bunch of stuff here. Now let's just go back and say substituting into our star equation. Let's see what we have. We have Q dot over M will be equal to what? We say that that will be equal to, that is equal to the 540 kilojoules plus H2 minus H1, so that would be 2675.6 minus 3231.7 minus the 7.8 that we calculated over there on top. So if we do this calculation, okay, I find that this is equal to minus 23.9 kilojoules per kilogram. Okay, so why do we know this? Why do we need this? If you remember, the question was to find the change in entropy. So what is the change in entropy equal to? We say that the change in entropy is the change of the entropy of the universe is equal to the change of entropy of the system plus delta Q over T. Okay? Over T over here. So that means that the change of entropy per unit mass of the universe, so let's say, would be equal to our Earth system per unit mass plus our delta Q over M divided by the T of the surface, or the reference temperature in this problem. So what is this one over here? If you remember, the units for S over here, I did not put them, but what are the units? These are kilojoules per Kelvin kilogram. Okay, and this is kilojoules per kilogram. So everything on the table is per unit mass. So this is really equal to what? S2 minus S1. And now this is a problem. This is the value we just calculated, which is 23.9. And this time the temperature is the only temperature that we have. Should be the temperature here given at the surface. Okay, so the 350. So T equal T surface equal 350 Kelvin. All right. So now comes here the issue about if this value is positive or negative. So this is our system. This is our turbine. So this is the control volume. And actually we found the value to be negative. So what does that mean? This is heat that is coming out. Okay? Out of the system. So that means this is energy that we won't be able to recover. So that this means that this term is going to increase the amount of energy being lost. So it's going to increase then the entropy. So even though this is a negative value, you see here is really increasing. If there is heat going in, what does that mean? We are adding energy to the system, and that energy will be in addition. So that energy will not be wasted. So it will be 23.9 divided by 350. So this will give us that the change of entropy of our system per unit mass will be equal to what? So HS2 is equal to 7.35 4.2 minus S1 6.9235 plus 23.9 over 350. And if we do the calculation, this is going to give us that the change of entropy to be equal to 0.4307 kilojoules per degree Kelvin per kilogram. So again, this is higher than 0 because not equal to 0. So that means that this system is irreversible. And again, this 0.4307 is like a quantity of energy that is being wasted in this process over here. Okay, so here pay attention, and it makes sense. If this energy going in is going to increase, is going to decrease the amount of energy being wasted because it's additional energy. But if the heat is coming out of the system, that's energy that we cannot recover. So that is going to increase the entropy. So if the Q is going in, then this value should be negative. Okay, so I hope that is clear. Thank you for your attention.